Artificial intelligence is rapidly becoming one of the largest new consumers of electricity in modern economic history. Every major breakthrough in machine learning, large language models, and cloud-scale computing depends on physical infrastructure that consumes enormous quantities of power. Behind every AI system sits a data center, and behind every data center sits an energy supply chain that must operate continuously without interruption. Plug Power's announcement that it is targeting up to 250 megawatts of hydrogen-based electricity capacity connected to the PJM market introduces a new dimension to the relationship between digital infrastructure and energy systems. At first glance, hydrogen may appear to be an unusual choice. By the laws of thermodynamics, hydrogen is not an efficient way to deliver electricity. Electricity is converted into hydrogen through electrolysis, stored as a molecule, transported or held in reserve, and then converted back into electricity using fuel cells or turbines. Each conversion step introduces energy losses. The round-trip efficiency of hydrogen power systems typically falls between 25 and 40%, meaning more than half of the original electricity input is lost before useful power is delivered. From a purely efficiency-focused perspective, hydrogen appears to be an unlikely candidate for powering one of the most energy-intensive sectors of the digital economy. Yet, serious capital is being deployed toward this concept, and the reasons behind this decision reveal important insights about the structure of modern energy systems. The growth of artificial intelligence is reshaping electricity demand patterns in ways that challenge traditional grid infrastructure. Data centers supporting AI workloads operate continuously, drawing large and stable power loads at all hours of the day. Unlike many industrial facilities that reduce activity outside working hours, AI data centers maintain consistent consumption because machine learning training and inference processes run continuously. As clusters of data centers are developed in the same geographic regions, electricity demand becomes concentrated at levels that local transmission networks were not originally designed to accommodate. Interconnection queues in attractive data center markets have extended significantly, in some cases exceeding 5 years before new facilities can obtain grid access. Substations designed for earlier demand levels must now support far greater electrical loads, requiring upgrades that involve planning, permitting, and construction timelines measured in years rather than months. This bottleneck is not caused by limitations in computing technology, but by physical infrastructure constraints within the electricity system itself. Hydrogen enters this discussion not because it is the most efficient energy carrier, but because it offers a pathway to bypass certain grid limitations. Electricity can be converted into hydrogen in locations where renewable generation is abundant or inexpensive. The hydrogen can then be stored and transported to the point of use where it can be converted back into electricity on site. This approach allows energy to be produced in one location and consumed in another without requiring immediate transmission capacity at the moment of generation. For data center developers facing delays in grid interconnection, the ability to deploy on-site power generation using stored hydrogen can represent a form of energy independence. The economic viability of this approach depends on whether the benefits of reliability and timing flexibility can offset the efficiency penalties associated with energy conversion processes. The technical pathway underlying hydrogen-based electricity supply begins with electrolysis. Electrolyzers use electricity to split water into hydrogen and oxygen. When renewable electricity sources such as wind or solar provide the input power, the resulting hydrogen is considered low-carbon or green hydrogen. Electrolysis systems typically require between 50 and 55 kilowatt-hours of electricity to produce 1 kilogram of hydrogen when accounting for system inefficiencies. At electricity prices around 4 cents per kilowatt-hour, the energy input cost alone approaches $2 per kilogram of hydrogen before considering capital recovery, compression, storage, or conversion equipment costs. Hydrogen must then be compressed or liquefied for storage, processes that require additional energy input. When hydrogen is later converted back into electricity using fuel cells or turbines, further efficiency losses occur. These cumulative losses contribute to hydrogen's relatively high cost compared to directly using electricity from the grid, when grid electricity is available at competitive prices. Plug Power's strategy extends beyond electrolysis alone. The company has invested in infrastructure spanning production, liquefaction, storage, and distribution, reflecting an understanding that hydrogen economics depend on integrated value chains. Hydrogen must be delivered reliably to end users with predictable quality and availability. Each stage of the value chain introduces both technical challenges and capital requirements. Compressors, storage tanks, pipelines, liquefaction equipment, and fuel cells all contribute to overall system cost. Coordinating these elements effectively is necessary to achieve competitive pricing for hydrogen-derived electricity. The PJM electricity market provides an environment in which hydrogen-based power must compete directly with established generation technologies. PJM coordinates electricity supply across multiple states, balancing supply and demand through competitive auctions in both day-ahead and real-time markets. Power producers submit bids indicating the prices at which they are willing to supply electricity. The lowest-cost generation sources are typically dispatched first, establishing market clearing prices that other resources must match or exceed to participate economically. Natural gas combined cycle plants provide dispatchable power with relatively low capital costs and established supply chains. Nuclear power plants deliver stable baseload electricity with high capacity factors. Renewable energy sources provide low marginal cost electricity when resource availability is favorable. Battery storage systems offer rapid response capabilities for balancing short-duration fluctuations in supply and demand. Hydrogen-based power must demonstrate economic competitiveness within this environment to achieve sustained deployment. Artificial intelligence demand adds complexity to this competitive landscape. Data center operators prioritize reliability, uptime, and operational continuity. Interruptions in power supply can disrupt digital services and result in financial losses. In some cases, operators may value resilience sufficiently to accept higher energy costs if reliability benefits justify the premium. Hydrogen-based systems can provide energy storage capabilities that extend beyond the duration limitations of battery storage technologies. Hydrogen can be stored for extended periods, enabling long-duration energy supply during periods when renewable electricity generation is low. This capability may become valuable as electricity systems incorporate higher shares of variable renewable generation. However, alternative technologies continue to evolve. Battery storage costs have declined significantly over the past decade, improving competitiveness in applications involving short to medium duration storage. Advanced nuclear reactor concepts are being explored as potential sources of stable, low-carbon baseload power. Natural gas generation remains widely available and can provide dispatchable electricity at relatively low cost in many regions. Renewable energy combined with storage can supply electricity with reduced emissions under favorable conditions. Hydrogen must therefore identify applications in which its characteristics provide advantages that cannot be easily replicated by competing technologies. Utilization rates represent another important factor influencing hydrogen economics. Electrolysis plants involve substantial capital investment that must be recovered through operational revenue over time. Facilities operating at low utilization rates produce less hydrogen relative to installed capacity, increasing the effective cost per kilogram of hydrogen produced. Data centers operate continuously, suggesting a steady demand profile that could support high utilization rates for hydrogen power generation if supply chains are coordinated effectively. However, variability in electricity prices and renewable generation availability may influence electrolysis operating schedules. System design must balance production capacity, storage capacity, and power generation capacity to maintain favorable economics. Policy frameworks may also influence the economic viability of hydrogen projects. Incentives supporting low-carbon energy deployment can affect investment decisions by reducing capital costs or improving revenue stability. Regulatory frameworks governing electricity markets can influence the participation of emerging technologies. Differences in policy support across jurisdictions can create varying economic environments for hydrogen deployment. Plug Power's strategy must consider these factors when evaluating project locations and timelines. Reliability considerations extend beyond cost metrics alone. Data center operators require power systems capable of maintaining consistent performance under diverse operating conditions. Hydrogen storage can provide resilience against supply interruptions by enabling on-site energy reserves. Fuel cells converting hydrogen into electricity can operate with low emissions while providing dispatchable power. However, system reliability depends on equipment performance, maintenance practices, and supply chain coordination. Reliability metrics influence technology selection decisions in mission-critical applications such as AI infrastructure. The relationship between artificial intelligence and energy infrastructure illustrates broader trends in the evolution of industrial systems. Digital technologies depend on physical energy systems that must adapt to changing demand patterns. Decisions regarding energy technology deployment influence investment flows, infrastructure development, and regulatory frameworks. Hydrogen represents one potential pathway for addressing emerging energy requirements, but its role will depend on economic competitiveness and system integration effectiveness. Plug Power's initiative demonstrates an effort to position hydrogen within emerging electricity demand segments. The intersection between hydrogen and artificial intelligence highlights the interconnected nature of technological innovation across sectors. Advances in one domain can influence opportunities in another. Hydrogen's potential role in supporting AI infrastructure reflects broader questions regarding the adaptability of energy systems to evolving economic activities. Evaluating hydrogen's prospects in AI-related applications requires examining multiple interdependent variables. Electricity input costs, capital investment requirements, technology performance characteristics, infrastructure availability, and policy frameworks all influence economic outcomes. The balance among these variables will determine whether hydrogen-based electricity supply achieves sustained deployment in competitive markets. Hydrogen may find opportunities in specific niches where its characteristics align with system requirements. Alternatively, competing technologies may prove more cost-effective in many applications. Plug Power's 250 megawatt initiative represents an exploration of hydrogen's potential role within emerging energy demand contexts. The initiative tests whether hydrogen's ability to provide long-duration storage and dispatchable low-carbon electricity can offset efficiency penalties associated with energy conversion processes. The outcome will depend on evolving cost structures, technological performance improvements, and market conditions. If hydrogen demonstrates competitiveness in applications such as AI data center power supply, it may expand into other sectors requiring reliable low-carbon energy. If economic challenges persist, deployment may remain limited to specialized applications where hydrogen's characteristics provide unique value. The interaction between hydrogen technology development and AI-driven electricity demand growth will influence the evolution of energy systems in the coming years. Understanding these dynamics requires evaluating technologies within system-level frameworks rather than focusing solely on individual components. Hydrogen's role in future energy systems will depend on how effectively it integrates with electricity infrastructure, industrial demand patterns, and economic constraints. Plug Power's initiative contributes to ongoing exploration of how emerging technologies can address evolving energy challenges associated with digital infrastructure expansion. The economics must ultimately determine whether hydrogen becomes a significant contributor to electricity supply for artificial intelligence data centers. The analysis requires examining cost drivers, utilization rates, infrastructure coordination, and competing technology development trajectories. Hydrogen's potential role remains uncertain, but the investigation itself reflects broader transformations in the relationship between energy systems and digital technologies.